Alright then, we have seen n number of properties till now, and properties are very essential while describing a system, while fixing a state. So we have seen properties such as temperature, pressure, internal energy, enthalpy, entropy, uh, and so on and so forth. There are many properties yet to come. There are a lot of properties which you may not be familiar with, such as Helmholtz function, Gibbs function, exergy, and so on and so forth. So there are large chunk of properties, huge amount of properties exist which are helping us to define a system, to fix the state of a system. Now, do we need to measure all these properties in order to fix a state? If we have to do that, then it's a big tedious task because there are hundreds of properties. And if you have to fix the state, if you have to know the state of some substance, say I have gas with me, some gas, I have air with me, so I want to fix a state at this condition right now, at this room temperature. So I have to go on measuring all these properties to fix the state of the air, to completely know what is the condition of air right now. Do we need to do that? Well, actually no, we don't need to measure all the properties. The same effect, the same work can be done just by measuring few of the properties. Just by measuring few of the properties. Why? Because once you measure few properties, once you fix these few properties, the other properties become dependent on these properties. In general, not all properties are independent for a given substance. For given substance, not all properties are independent, they are depending on each other. So if we could find the number of independent properties, and if we could measure just those properties, then we don't need to measure other properties. Just by knowing those set of properties, we will be done. So how much are those properties? What are those properties? And are they same for all the substances? Well, the answer is given by the Gibbs phase rule. The equation of Gibbs phase rule is n of I plus phi is equal to C plus 2. So n of I is number of independent intensive properties. Phi represents number of phases that exist in the system. C represents number of components that is existing in the system. And then we have just the number 2. So this is an important equation given by Gibbs phase rule. Okay, let's just apply our equation onto our first substance, which is a gas. Right, any gas it might be. So for gas, what are the number of phases? How many phases in which does the gas exist? Well, it exists in only one phase, that is the gaseous phase. How many components are there? Just one component. So by putting these values, what we get, n of I is equal to, this 1 and 1 gets cancelled, is equal to just 2. So the number of intensive properties that are required to fix the state of a gaseous substance are only 2. What does that mean? That means that if I have this container and I have gas entrapped in it, it might be in any condition, it might have any set of properties. So any properties it might possess any values of these properties. But to know the condition of this gas completely, what you need to do, just measure the two properties. Which two properties? Any two properties, and you're done. So all you need to do is just measure any two properties. Maybe you can insert a thermometer, measure the temperature, insert a pressure gauge, measure the pressure, and you're done. All other properties will be automatically fixed. They will be dependent on these two properties once you know pressure and temperature. And that is why if you have explored and seen, you would have noticed that mostly for gas, for any gaseous substance, a two-dimensional graph is drawn, a two-dimensional plot is drawn between the properties. So why do we do that? Because two properties are sufficient to fix the state. So whenever we do this, we mark the state here, right? So this represents some value of pressure and this represents some value of volume. Okay, so the graph here is not just representing pressure and volume. It is not limited to only this information, but it is also representing all other properties as well. For example, if this is given by, maybe we have this isobaric process, this can also be represented by a TS chart. So we measured pressure and volume, we never measure temperature and entropy, but still we can go on plotting this onto this chart. So it will be something like this. So if we have multiple pressure lines, constant pressure lines, so there will be something like this. Okay, diverging pressure lines. And similarly, if you have constant volume process, this is a constant volume process that I'm drawing now. This also can be represented by TS or any other two property diagram. The equivalence of this would be seen on this. So here also volume be something like this. All right, so for gases, two properties are sufficient to fix the state and to know the entire condition of the gaseous substance. All right, so let's go on to our second example where we have two-phase substance. So what is a two-phase substance? We are considering water here. So water, when it is about to boil, it exists in liquid as well as vapor, right? It exists in both. So here number of phases become 2. So let's just use our equation n of I plus number of phases is equal to number of components plus C. Now here, since only one component is used, we are taking the example of water. So this is 1 and 5 becomes 2. So n of I comes out to be 1. That is even lesser. So fixing just one property, you are done. For a two-phase substance, for a substance for water which is about to change its phase, can be completely described by just a single property. Now, and this is true also because when you say boiling temperature is 100 degrees Celsius, automatically the pressure at which boiling is happening is also fixed. It is 1 bar. It is atmospheric temperature, right? At atmospheric pressure. So if you change this, this also changes accordingly. So just by representing one property, just by measuring one property, you are describing the entire phase change process. So this is something like this. Let me take an analogous example, a daily example. When you say that the day is sunny, the sun is well above your head, it is shining bright, so it is a sunny day. Once you say that, you need not to say, you need not to specify separately that rain is absent or maybe cloudy weather is absent or maybe snow is absent. So this chunk of information automatically gets fixed when you say that the day is sunny. So here the Gibbs phase rule does something like this. Once you specify number of independent components, number of independent properties that are sufficient, then you are automatically fixing the other properties also. So once you measure two properties for a gas, other properties also become fixed. Okay, here let me also go into the definition of state, which says that number of independent properties which are required to completely describe the system. Now you know the significance and the meaning of this sentence, right? Because there are certain number of independent properties which are sufficient to describe the entire system, and that is what we know from the Gibbs phase rule. Alright, so state is nothing but once you fix certain number of properties which is given by Gibbs phase rule, your condition of this system is fixed and you are done. There is also another term called as state postulate, which is number of properties required to fix this state, which is similar to what we found from Gibbs phase rule. So number of independent properties which are enough to fix the state is called as state postulate. Now again note that fixing a state essentially implies that you are completely describing the system, you are understanding the condition of the system. Yeah, so let me just end this video here. Thank you for watching.